Hello students, in Fluid Mechanics 2, we will start with the topic Viscous Incompressible Flow. As you can see, before starting the topic, you have already completed one full-fledged course in Fluid Mechanics, that is Fluid Mechanics 1, in which typically you have started with the properties of fluids, then fluid statics, and after that you moved on to kinematics of fluids, followed by fluid dynamics, typically considering incompressible flow as well as inviscid flow. That means there is no viscosity, which actually resulted to your very well known Bernoulli's equation. And after that you probably you have gone through the different devices, that means different measurement devices to measure the pressure as well as the flow using or utilizing the Bernoulli's principle. So after that you had some exposure in pipe flow, in which you again introduced to the viscous effect, typically the effect of viscosity, and that is what you had as Hagen-Poiseuille equation, that is the pipe flow equation, or flow through circular conduit. So there in Fluid Mechanics 1, at the later stage, you were introduced to a kind of a viscous incompressible flow, a little bit in terms of pipe flow, and afterwards you actually had some exposure in open channel flow. So that was your typically Fluid Mechanics 1. In Fluid Mechanics 2, our objective is to look into the fluid mechanics problem where the different force interactions are taking into account in order to design different devices, different kind of devices. For example, say the different motion vehicles, be it aero vehicles, be it underwater vehicles, be it floating vessels, or be it automobiles running on road. In all the cases, we know that all the moving vehicles actually they encounter fluid. I mean, they have to go through the fluid medium, be it air or water, whatever, and whatever be the fluid, they always offer some kind of force which opposes the motion, what we call as drag force. So that actually you need to design the vehicle in such a way that this resistive force or the resistive effect should be minimum, so that you can save some amount of fuel. So that is what we call as, you need to increase the fuel efficiency. That is one very broad area of fluid mechanics through which understanding of proper fluid mechanics will lead to a good design of those kind of vehicles, which actually leads to some kind of energy saving. So that is one broad aspect of fluid mechanics. In Fluid Mechanics 2, we are going to look into some kind of very fundamental situations from where we can get the idea of how these different kind of force or thereby the different kind of opposing effects are generated. And another aspect of Fluid Mechanics 2 is to understand the different effect of properties which otherwise we neglected in our Fluid Mechanics 1. For example, the viscous effect, that is what we are going to start, that is viscous incompressible flow. For example, the compressibility effect. In most of the cases in Fluid Mechanics 1, we dealt with the fluid to be incompressible, that is basically the density to remain constant. And also the flow by and large we considered to be inviscid, that is the viscous effect we neglected only in Hagen-Poiseuille equation you considered the effect of viscosity. Otherwise, it was all through inviscid flow. And another aspect that we neglected broadly, or mostly, if not wholly, that is the flow to be steady. That means the temporal or local component of acceleration all through in your fluid mechanics 1 was neglected. Here in our fluid mechanics 2, also by and large we are going to neglect the effect of this unsteady part, that means this temporal or local acceleration part. But here we will have one particular topic which is known as unsteady flow, where we will look into the effect of this temporal or local acceleration. So that is basically where actually we are going to look into other aspects of fluid mechanics which were otherwise simplified in your fluid mechanics 1. So let us start into the first topic. As I said, that it is viscous incompressible flow, where by we need to look into the effect of viscosity. And this topic, there are some simple situations which we will actually going to understand, and those are bulleted here, written in bulleted form. That is, first of all, flow between parallel plates. This is one kind of situation which we will look into, followed by flow through pipes. This pipe or Hagen-Poiseuille equation. Already in my statement you heard about this Hagen-Poiseuille equation, which we have learned in fluid mechanics 1. So why going to repeat that? This repetition is basically a kind of recapitulation by using the Navier-Stokes equations. Now you are already having the notes of this Navier-Stokes equation. So where it is actually the equation of motion for incompressible flow in Cartesian frame of reference, or you can also derive that particular incompressible flow equation of motion in cylindrical frame of reference as well. So this derivation in detail actually are being provided in note form, so I am not going to repeat it. It's basically considering the stress, shear stress and the normal stress, along with the body force term, that is the external force actually is contained by this body force and surface forces. Those forces you need to configure, and that should be equated with mass into acceleration. So this is basically the very simple Newton's second law of motion, which has to be applied in a three-dimensional Cartesian frame of reference in a control volume of elemental size delta x, delta y, and delta z. And then basically we did the step-by-step derivation and also by using Stokes' law of viscosity, we ultimately arrived to the equation of motions in differential form. So these are the final form of equation of motion in x direction, and in the other two direction, that is y and z direction. Okay, so that is what is being written here, and already I think you have gone through that. So we will be referring this particular equation of motion, and this equation of motion is also known as Navier-Stokes equation. So here in our second part of the situation, that is written as flow through pipes, which is a recapitulation by using that Navier-Stokes equation. And the third one is flow between two concentric cylinders. So these are the three situations that we will look into, either by using Navier-Stokes equation or through control volume or CV approach, typically the approach that you had in your fluid mechanics 1 while deriving several situations, out of which one was your Hagen-Poiseuille equation, of course. So coming into the first situation, that is flow between parallel plates, in which we have some assumptions. Let us look into those assumptions. First of all, the flow here is assumed to be steady, laminar, and the two plates through which flow is occurring, as you can see here, a sectional view of this particular situation is shown, where the plates are being considered to be infinitely expanded, so that the end effects can be neglected, and also the variation in z direction is neglected, such that we consider the flow to be a two-dimensional flow. Further, we consider the flow to be incompressible, as by the heading it is viscous incompressible flow. So even if it is not mentioned in any case that the flow is incompressible, under this chapter, under this topic, all the flows are considered to be incompressible. That means the density is not going to change, and it is fully developed laminar flow. So these are the four major assumptions in the case. And what do you mean by fully developed laminar flow? It is basically whenever a flow is being entered into a particular cross section from another cross section. So initially the flow actually is being accelerated or decelerated. That means it is going to change its parameters. So and it will take some length or some distance to get stable or to get developed. So that particular distance up to which the flow is changing its characteristics in terms of the velocity profile, that particular distance is what we call as the developing length or entrance length. So here you can see if x equals to 0 is the starting point of our the plate, where x equals to 0, and here we can have the velocity profile as uniform. That means you can say that all through this particular distance between the two plates, the velocity are same, represented by same length arrows. At a certain distance, x equals to x1, you can see that the velocity profile from this gets into this particular profile due to the reason it comes in contact with solid boundary. The two plates are being fixed, or it is stationary, through which you are actually forced the fluid to flow. So when the fluid particles come in contact with the solid boundary which is fixed, so it will try to adhere, or it will try to attain the velocity of the solid boundary itself, what we call as the no-slip condition. So due to that, actually at this boundary, the flow velocity will become equals to 0. So there must be a gradient due to which from 0 velocity to the maximum velocity, the velocity of fluid particles will vary like this, and there will be interaction in terms of the viscous effect, or due to this viscosity, it will basically change the velocity profile. So this change will take place at different distance, x equals to x1, and then at x equals to x2. Some representative velocity profile is shown here. So it is further being changed, and you can see at x equals to x3, the velocity profile may looks like this, and it is this x equals to x3 onwards you may have this particular velocity profile to prevail. So thereby we can say that x3 is the fully developed length, beyond which the velocity profile does not change any further. Okay, so that is our consideration, or our analysis starts from this point onwards. That is our x equals to 0 is actually x equal to x3. So from here onwards, in the direction of flow, the velocity profile is not changing in x direction. Or another way, in fully developed flow, we can say that del u del x, that is the gradient in x direction, is equals to 0. Okay, so that is a very important consideration, and the significance of fully developed flow. The moment you state the flow to be fully developed, it actually indicates mathematically this del u del x equals to 0. Okay, so then let us move on to further mathematical derivation part, and we are having in our hand two governing equation or two constitutive equation. One, that is the continuity equation, and the other, of course, the equation of motion. So the continuity equation for incompressible flow in three-dimensional case is del u del x plus del v del y plus del w del z. So as we are not considering the z effect, that means as it is infinitely expanded in the z direction, so we consider there is no change in z velocity or z component velocity, and any property with respect to z is not changing, that is del z of anything is 0. Okay, so thereby the 2D flow continuity equation, incompressible flow continuity equation, is this one. And then as for fully developed flow, this del u del x is 0, just now we have agreed. So thereby del v del y is equal to 0. So that leads to v to be constant in y direction, of course. Now the boundary condition at wall, what is that boundary condition? Is basically the condition where you know the property and you know the other characteristics of flow in terms of velocity or temperature, whatever. So that is what we call as the boundary condition. So at wall, that is at the two plate, at y equals to 0, we have v equals to 0. So if at y equals to 0, v equals to 0, and you are having del v del y equals to 0, so we can say that v equals to 0 for any y, as it is not changing with y. So thereby for x greater than or equal to x3, that means at the fully developed region, we are having the definition of the velocity vector as this v equals to I cap u in vectorial notation. So the equation of now coming into the equation of motion or momentum equation, that is basically the Navier-Stokes equations you had in 2D flow, in 2D form. In x direction, it is u del u del x plus v del u del y is equal to minus 1 by rho del p del x, that is the pressure gradient term, and the viscous term as this new, that is the kinematic viscosity, as it is divided by rho, mu by rho, and bracketed term is del 2 u del x2 plus del 2 u del y2. Here the body force term, that is fx term, is not being considered in the direction of flow. Okay. So now putting the different considerations, that is for fully developed flow, del u del x equals to 0, and you are having v equals to 0, we obtained from continuity equation, so it is put as 0. And in a similar manner, as you are having del u del x equals to 0, so the higher order derivative del 2u del x2 also set equals to 0. So that it leads to 1 by rho dp del p del x, 1 by rho del p del x, that is the term which remain, and this new del 2u del y2. So this is basically the term which we need to retain in the x direction Navier-Stokes equation, that let us say we name it as equation 1. In a similar manner, momentum equation in the y direction, if you consider, then it will be u del v del x plus v del v del y is equal to minus 1 by rho del p del y plus nu del 2v del x2 plus del 2v del y2. Here also we neglect the body force term Fy. Now as v is 0 also, so del v del x and this term, this left hand side term also will be equals to 0, and the viscous term also, as it is del 2v del x2 and del 2v del y2, these also gets equals to 0. So the only term that remain is our del p del y. Here there is a mistake which we can correct it. It is actually wrongly written as del p del x. It should be del p del y. Okay, so in the note I believe it is written as del p del x, so it should be corrected. Okay, so this term actually is del p del y, which is the only term that remained in this equation of motion in y direction, so that is set equals to 0. That actually indicates this pressure P is a function of x only. This pressure P is a function of x only. So once it is a single variable function, so we can write del p del x as dp dx. Also, as you are having your u, the velocity is only a function of x. So so basically del u del x can also be written as du dy. So then equation 1 now can be written as 1 by rho dp dx is equal to nu del 2u del y2. So this is the equation 1, which now can take this form such that dp dx can be written as mu d2u dy2. So this is equation number 3, let us say, and it is actually constant because, as you can see, the form of this equation, the left hand side is a function of x and the right hand side is a function of y. So basically these two are separate dependent variable. It is only possible if they are being equated. It is only possible once they are constant. Anyway, so if we now integrate this equation 3, as you can see, we obtain the velocity expression, that is u velocity, that is equals to this form containing two constant, as it is twice integration, two integration del 2 d2 u d2 dy2. So you need to integrate first to get du dy and then u. So now our task is to find out this c1 and c2, the two constant. How to find it out? We need to find it out by imposing the boundary condition. To know first of all the boundary condition properly is a very important aspect of different fluid mechanics problem. So here if we refer back to the figure, what we can see is as per consideration of our coordinate system, the frame of reference we have fitted. So here it is actually y equals to 0, and then it is here it is y equals to b. Okay, so this is my y equals to 0 and this is my y equals to b. At both this point, it is the boundary actually of the plate where by no slip condition the velocity has to be 0. So the wave boundary condition is written here. You can see at y equals to 0, u equals to 0, y equals to b, u equals to 0. So by no slip condition. So that has to be written. Why I am writing this boundary condition? By no slip condition. So once you have these two conditions known, you are having two equations, so two variable, two unknown. So you can solve it very easily, and that leads to C2 equals to 0 and C1 equals to minus b by 2 mu dp dx. So these two constants, if you substitute in this equation 5, will give you ultimately the velocity profile, what we are calling, and this is the expression in this black box. You can say it is equation 6 is the velocity profile for what type of flow? For flow through parallel plates, and more specifically we can say the flow through two stationary parallel plates, infinitely expands parallel plates. Okay, so and also you can get the condition of maximum velocity, means we need to put this du dy equals to 0. So if you find this du dy, it is being like this, and at what condition this becomes equals to 0, that is at y equals to b by 2, this du dy comes equals to 0. So therefore we can say that u will be maximum when y equals to b by 2. Okay, so this from equation 6 we can find out this u at y equals to b by 2. That leads to another black box containing this u max as equals to minus b square by 8 mu dp dx. That is what we are calling as equation 7. Now one thing here you can see it is negative. Why this negative sign? I mean, that is nothing but because of this dp dx. This dp dx term, actually if you find it out, you will see that it would be negative because it is always in the direction of the flow pressure head, or the pressure falls. So that's why if x is my direction of flow, my dp will be negative. So that is dp dx equals to negative. So both negative will get cancelled out, and you get ultimately to be u max to be, or u to be positive always. So that is the reason why you are getting it as negative. Already it is written here also for your convenience. Negative sign is due to the fact that dp dx will be negative. So once you get this u, that is the velocity, then you can also find out the discharge for a width say w, for a width w of the plate. That means now from infinite, say this is the, so this is basically your plate width, means, so this is the two plate where, okay, so this is the two plate through which your flow is occurring. So okay, so which one is your w? I mean, here this is basically your b, and this is your width we are considering. In some books you will find this discharge to be written per unit width. Okay, so this dimension, if you know, then you can just multiply to get the flow for that particular width. So anyway, here if we are considering this width to be, w, so we can write q as equals to integration over 0 to b, because my velocity is a function of y, where y varies from 0 to b. Okay, there you can see u is a function of y, and it varies from 0 to b. Y varies from 0 to b. So that is why my integration limit is 0 to b. It is u dy into w. So it is the elemental strip in between somewhere. You can consider an elemental strip. This is the elemental strip of width, this length b dy, and the width is w. That is why this area, elemental area, is w dy. So that if you put the expression u here, so you get this thing. So this integration, ultimately will lead to the expression of q, that is minus wb cube by 12 mu dp dx. So again here once again it comes to be negative as usual because of the expression of u. It will be negative as it contains dp dx. Once you get the value of dp dx, it will automatically get its positive sense. So this is how we can find out the discharge. And then if now for a channel, for example, for a channel of length L and having a pressure difference P1 minus P2 across this length L, then the velocity can be written as this: P1 minus P2 by L is my dp dx, and every other thing remains as it is. So the discharge also can be found in terms of this P1, P2 and L. This is how you can evaluate it. And also once you find this Q, you can also find out the U average. U average also you can evaluate. That is basically Q by area, the way we write it typically for steady state. And we are dealing with steady state flow here all through. So if you find out this Q and you know this area, here area will be W into B. So this is actually W into B. If you put it like that, you find this U average. Here Q you need to put as this, if in this form P1 minus P2, or in this manner also you can put to find out the average velocity, and thereby you can also find out this U average by U max, what is the ratio it is coming. Okay, sometimes it has some non-dimensional manner. Sometimes we need to put in this fashion. Okay, so the fundamental thing is that you need to find out first the velocity expression or the velocity profile, and then the discharge, and then whatever you want you can find out. So this same relation, whatever we have found up to equation 8, you can also find it out by using the control volume approach. Okay, so that approach already is being you can find in book that is in Massey or any other a bit in that approach written book. In Massey actually there is no Navier-Stokes equation. You will find all the derivations are using this elemental control volume approach. Okay, so where actually a small rectangular element of the fluid with sides parallel to the coordinate axis have been considered, and that is basically delta y is the thickness which varies from 0 to b, and the velocity at the bottom part is u and the top part is u plus delta u. That is the gradient of velocity due to viscosity. You are having this kind of thing for a laminar flow. So there is no movement in the fluid in any direction perpendicular to the flow, and this is the approach where you can get the same thing. And this is the structure of the elemental volume. In this figure you can see tau, it is acting in this direction, and in the other layer the shear stress is acting in the opposite direction. So that is basically is the shear deformation due to which the flow is occurring, and the magnitude also varies from tau to tau plus delta tau. And on the other two sides we are having the pressure, that is P star, as the piezometric pressure which incorporates the gravitational head as well, or the gravitational corresponding elevation head. The pressure is being incorporated. That is what we call known as the piezometric pressure. So this pressure is varied from P star to P star plus delta P star. So in this control volume we are having two surface force in terms of the shear force and two pressure forces and acting on the respective area, and that has to be summed up to get the net force, and which should be equals to 0 because of no acceleration as the flow is steady. So that is what is written here in this manner, so that you get ultimately, I'm not going through this each and every steps. I think these are very straightforward to understand. So ultimately, you can see this is the form you get. And then for Newtonian fluid, you have the definition of this stress with respect to viscosity and the velocity gradient. That is well known, Newton's law of viscosity, that is this one. So here this has to be replaced in tau, so that it leads to mu del 2u del y2 is equal to delta p star del x delta x. So that when this can be integrated, if you integrate it, you will lead to the same form of the velocity profile that we obtained using Navier-Stokes equation. So that is this I am talking about, which is here denoted as equation 12. So this equation 12 and equation 5, if you look back into equation 5, it is the same thing. Coming into that, yes, it is the same thing. It is the same form of equation, u equals to 1 by twice mu dp dx y square, or it is written as 1 by mu dp dx into y square by 2, the same thing, plus c1y c2. So here also you can see equation number 12, 1 by 2 mu delta p star. Only difference is that it is written in piezometric pressure form. It doesn't matter here. In your earlier Navier-Stokes equation, we actually not considered the elevation head, so the body force term as 0. So it can be put inside the pressure as piezometric pressure if it is only the gravitational pressure you are going to consider, or the gravitational head converted into pressure form. Okay. So otherwise, this form is same. It is exactly the same thing that one can obtain, and hence this point onwards, it is no reason to go further to do the same thing, the same repetition. Okay, the approach, it will be the same thing once you reach to this form. The rest will be same again. You need to apply the boundary conditions and so on and so forth. Okay, so that is the way. You can approach using Navier-Stokes equation. You can approach using the more classical this elemental volume concept, and then utilizing certain fundamental laws. Nevertheless, you will reach to the same conclusion, or you will reach to the same form of the equation, whatever you do. Sometimes these Navier-Stokes equations are, convenient, but not all the time. Navier-Stokes equations may be convenient to use in a particular situation to arrive at a particular form. Okay, so here we will look into the situations using both the approaches, so that you can get exposed to different type of application of this situation. Okay, in some books you will find these are known as exact solution of Navier-Stokes equations. These are the situations where you can have exact solution of Navier-Stokes equation. Anyway, so extending the situation of flow through parallel plates, we can have a special case, or another case which is known as quiet flow. That is basically the situation where one plate remains stationary and the other moving at a constant velocity. So that is the difference with respect to the other, where both the plates were stationary. So what essentially it changed actually is the boundary condition, isn't it? Because in the other case, we started with Navier-Stokes equations, and at the boundary condition we put y equals to 0 as u equals to 0, and at y equals to b, u is equal to 0. But now, by definition, you are having the upper plate, for example, as it is shown here, is moving with a constant velocity up. So at y equals to b, here instead of u equals to 0, we are having u equals to up. So that is the change that takes place when you are having a quiet flow. So actually we started here from U equals to this, U equals to this form, that is the definition or the expression of velocity profile obtained either from Navier-Stokes equations or by the control volume approach. That is your equation 5 or 12. And then you put the boundary condition like what is written here, and that leads to the expression of u in another black box as u equals to this. So this is the changed or modified expression of velocity profile as one can observe with respect to the previous one in whatever approach you do. Okay, that is denoted as equation 13. Okay, so this is the quiet flow velocity profile. Now if you are asked to find out the velocity profile for quiet flow, you should not definitely start from this form. You need to arrive at this form if you are asked to find the expression of quiet flow in exam. But here, as it is a continuation, I am taking the advantage of starting from this form. Okay. So once you get this velocity profile, you can observe that this velocity u is having an additional term, that is this term, which was absent in the previous one, flow through parallel plates. Okay, so up till now, whatever we have done is we actually started to look into the situation of viscous incompressible flow from two different way. One using Navier-Stokes equation or equation of motion, the general equation of motion for incompressible flow, and also using the more fundamental control volume approach. Okay, so in the next lecture we will look into the other two situations. Okay, so thank you.